Hello, welcome back to the stochastic processes class. My name is Sondolo Afemi Golugui, and today we will check one of the powerful tools we'll be using in stochastic process, which is matrix. And then in these sessions, I just want to do a quick revisions on matrix. Okay, because that is one of the powerful tools we'll be using in the course of this course. So let's first of all take the notation. Let's first of all deal with the notation before we move on. So let's say let A be an n by n matrix. That for it to be n by n matrix, that means that we are talking about a square matrix. So this our matrix A. We can write it as A, then subscript ij, or we can write its component or its element as A I j. So take note of this three notation: matrix A, then its component we can write its component like this, and we can also write its component also like this. So if you want to put in the matrix form, you have your matrix bracket, then you have your A index ij, whereby your row is your I stand for row. Let me write it here. That is your row. Then your column J is a column. So take note of that. So that's the first notation I want you to take note of. So with this now, you're able to that. So that means that if we can now move on to matrix multiplication, but please take note of this notation, very, very important in the course of this particular course. So let's go to matrix multiplication. In matrix multiplication, if we have our matrix A, which we can write it as A index ij, I mean the element of aij. Then we also have, let's put this in bracket and that's to make it more better. And we have our B and B, matrix B, which can also be written as ij equals to B subscript ij. So the multiplication now, if your we have a matrix, let's say 3 by 3 matrix now. A 1 1, A 1 2, A 1 3. That is column 1, row 1, column 1, row 1, column 2, row 1, column 3. And we have row 2, column 1, row 2, column 2, row 2, column 3, row 3, column 1, row 3, column 2, row 3, column 3. Then we have our B. As will be B row 1, column 1, row 1, column 2, row 1, column 3, row 2, column 1, row 2, column 2, row 2, column 3, row 3, column 1, row 3, column 2, row 3, column 3. So in dealing with the multiplication now, that will be row by column. That is this times this, A 1 1, B 1 1, plus this times this, that is A row 1 column 2 times B column 2 row 1, and this times this, plus A row 1 column 3 B column 3 row 1, and etc. So we can actually write this in form of summation. A multiplication of AB matrix AB, which is the same thing as Aij times B index Ij equals to summation. So we see that we have our row 1 is not changing, row 1, row 1. So, and that is I. So we can see that, and the column for our A is changing. It moves from 1 to 2 to 3. So let's take that as K, and let's take K equals to 1 to the number of matrices we have, n by n matrix. Then we have our B also. For our own B case, it is the column that is changing, that is increasing rather, which is 1, 2, 3. So we take that to K, and our column of the row of our B is not changing, while the column is fixed. The row is changing, while the column is not changing. The row is changing, the column is not changing. So we have that to be J. So that is how to write the summation of a matrix. So if we now take our B, if we take B to be A, that is B, we substitute B for A, then we are going to have A times A, which equals to A Ij times A index Ij, and I can just write this as A times A squared subscript Ij. Then we are going to have summation K equals to 1 to n number of matrices. You have A subscript I K, A subscript I K J, and that will be our result. So take note of this particular notation. We will actually need it in our next class, whereby we'll be checking the T-step transition probabilities of our stochastic process. Thank you for watching. See you in the